It had witnessed planets crack apart and stars blaze into existence. It had skimmed past supermassive black holes and quasar jets capable of shredding entire galaxies. It had crossed light years of absolute nothingness and glimpsed, just barely, the edge of everything. And now, more than 4 billion years after that epic journey began, the probe had finally come home. The sun was unrecognizable. Swollen into a bloated red giant, grotesque and violent, it had already swallowed Mercury and Venus whole. Earth survived, but only as a scorched, tattered mass of iron and nickel, tumbling in a decaying orbit dangerously close to the dying star. What remained of humanity, barely 100 million souls, had found refuge on Europa. The heat from the expanding sun had long since melted that moon's ancient ice, and now this small world circling Jupiter was the last sanctuary they could reach. It took the probe several minutes to decipher the strange language of the signals drifting up to meet it. The remaining humans, it seemed, buzzed with something between curiosity and desperate hope. They remembered the probe, even across all those ages. A memory preserved like an ember through the long dark. Humanity had tried again and again to spread itself across the stars. Every colony attempt had failed. Machines could cross the interstellar void, but every time living people dared that crossing. Through the vast, cold nothing between the stars, their fragile bodies gave out. As far as anyone knew, this small cluster of survivors on Europa was all that remained. And as the swelling red sun constantly reminded them, time was running out. But they also remembered something else. Long ago, interstellar probes had been built. Machines threaded with artificial intelligence, as sharp and capable as any biological mind. These probes had been sent outward with a purpose: to catalog the universe, to uncover what no telescope ever could, and to see the largest, the most extreme, and the most bizarre things in existence. And all of that searching, all of that measuring, had been in service of one greater goal: to find a way for humanity to travel beyond its solar home. Millions of probes had been launched across the ages. Only one had returned. And so, fulfilling the promise made to creators long dead, the lonely probe began to tell its story. A story spanning billions of years, relating everything it had learned, everything it had witnessed, every remarkable place it had been. It began to describe everything within the universe. The probe had named itself Batuta, after the great 14th century explorer Ibn Batuta, who, over 3 extraordinary decades, had traveled across nearly the entire known Muslim world, covering more than 117,000 kilometers, outpacing every great wanderer of his era, including Marco Polo. For a machine about to venture into the seemingly endless black, the name felt right. But before leaving the solar system, it had to prove itself. Batuta had 1,000 siblings, each as intelligent, each as capable. Only a select few would be granted true autonomy beyond human oversight. Those who failed the trials would spend eternity within the solar system. To earn its freedom, Batuta had to demonstrate it could survive extreme conditions, devise clever experiments, and coax nature into revealing its deepest secrets. It began on Titan. Titan, the largest of Saturn's moons, had been discovered by Dutch astronomer Christian Huygens in 1655, using a telescope he had built himself. Huygens was one of the towering figures of the scientific revolution, and remarkably, one of the first people to seriously consider whether life might exist on other worlds. He wrote that some planets might be home to rational creatures of different kinds, possessing different degrees of reason. Little suspecting that the very moon he had just spotted could be a candidate. Centuries later, in 2005, a small probe, not even 3 meters wide, detached from the Cassini spacecraft and began its 22-day coast toward Titan's surface. Named after Huygens himself, the lander used a parachute to slow its descent through one of the most extraordinary atmospheres in the solar system. Of all the rocky worlds beyond Earth, only Titan and Venus host a thick, significant atmosphere, and only Titan would receive a visitor from the inner solar system that day. Huygens touched down gently, leaving a small impression in the icy surface before bouncing to a stop. For the first time, humanity had placed an emissary on the surface of a world in the outer solar system. And what a world it turned out to be. Titan is 50% wider than Earth's moon and 80% more massive, a worthy bearer of its mythological name. Its core is mainly rock, surrounded by a crust of ice, wrapped in a dense atmosphere even thicker than Earth's. Surface pressure on Titan is about 50% greater than what you feel at sea level on our planet. But the most astonishing feature of Titan is the one thing it shares with Earth that no other world in the solar system can claim: liquid. On Titan, there are rivers, streams, estuaries, and deltas. You could stand on the shore of a lake, feel gritty sand beneath your feet, and watch waves lap at your ankles. But the temperature is nearly 200 degrees Celsius below zero. Those lakes are not water. They are filled with liquid hydrocarbons, methane and ethane. The rain falling from the orange sky isn't water droplets, but hydrocarbon compounds, evaporating and cycling back down in a process eerily parallel to Earth's own water cycle. Yet kilometers beneath your feet, locked beneath Titan's ice crust, there is something more familiar: a liquid water ocean, kept from freezing by internal heat and the presence of ammonia. Titan is the only world known to host liquids, both on its surface and hidden deep within. This makes Titan a candidate for not one, but two kinds of alien life. The first kind would be life as we know it. Biology that uses water as its solvent, the universal medium in which Earth's chemistry operates. But the hydrocarbon lakes on the surface could support something stranger: a biochemistry operating at 200 degrees below zero, using ethane or methane instead of water. Life beyond our imagination, living in conditions we once thought impossible. Titan is not alone in hiding a secret ocean. Enceladus, one of Saturn's smaller moons, barely 500 kilometers across, also harbors a vast liquid ocean beneath its frozen shell. Europa, Callisto, and Ganymede, all moons of Jupiter, likely contain more liquid water than all of Earth's oceans combined. Even distant Pluto, clinging to scraps of warmth from radioactive decay in its core, may host a subsurface ocean. But reaching those oceans is a challenge that dwarfs any engineering humanity has ever attempted. In the outer solar system, water ice is as hard as granite. Worlds like Europa may be encased in ice sheets over 100 kilometers thick. Upcoming missions, such as the European Space Agency's JUICE spacecraft and NASA's Europa Clipper, won't even try to pierce those shells. Instead, they will orbit and sample the plumes of cryovolcanoes, where active geological forces vent material from the interior into space. If biology stirs in those dark oceans, molecular signs of it may rise with those plumes. The Huygens lander transmitted 90 minutes of data before Cassini moved out of range, and the signal was lost. The probe was designed to survive Titan's surface conditions, and most likely it still rests there today. A quiet, solitary monument from a distant, forgotten time. Before Huygens made its daring descent, Cassini itself had already been gathering extraordinary data about the outer solar system. Among its achievements is a stunning color image of Jupiter's Great Red Spot, captured exactly 335 years after the storm was first documented by the scientist after whom the spacecraft was named. The Great Red Spot is a hurricane of staggering proportions, winds screaming past 400 kilometers per hour, a storm that has raged for centuries. At its historical peak, it could have swallowed 3 Earths. Recent analysis of older measurements suggests the storm visible today may actually be a different, younger system, less than 200 years old, rather than the original feature observed centuries ago. Enormous, yes, but clearly not eternal. This storm isn't powered by sunlight. It draws its energy from Jupiter's own interior. Jupiter actually releases more heat into space than it receives from the sun, the result of a process called the Kelvin-Helmholtz mechanism. As the planet slowly cools and contracts, compression generates heat that can only escape through the surface. And because Jupiter is so immense, this process will continue for billions of years. Cassini continued operating for 12 more years after Huygens fell silent on Titan. Its end came in 2017, in what mission controllers called the grand finale. A series of daring passes between Saturn and its rings, collecting as much data as possible before the inevitable. NASA didn't want to risk contaminating Saturn's moons, so Cassini was directed into the planet itself. On September 15, 2017, it plunged into Saturn's atmosphere, a journey of nearly 20 years and 8 billion kilometers ending in fire. Before it died, Cassini captured one final image of the storm system that had puzzled astronomers for decades. a near-perfect hexagon sitting atop Saturn's North Pole, first spotted by Voyager 1 in 1981. That strange geometric shape isn't an alien artifact. It arises from Saturn's complex wind dynamics. Different latitudes, blowing at different speeds, triggering instabilities that produce a ring of cyclones surrounding the pole, all working together to spin a gigantic vortex. Like a ring of hands pushing a merry-go-round, they maintain the hexagonal shape with eerie precision. These storms, grand as they appear from above, are relatively shallow, a few hundred kilometers thick at most. Beneath them churn even more violent systems, hidden from view, were it somehow possible to descend into the atmosphere of a gas giant, past the cloud tops, through the deepening pressure. A traveler would eventually encounter something that exists nowhere else in daily human experience. At around 4 million times atmospheric pressure, hydrogen atoms destabilize. The protons arrange themselves into a repeating lattice, and the electrons roam freely among them, the very definition of metallic behavior. At these depths, hydrogen becomes a metal. This was predicted theoretically in 1935 by physicists Eugene Wigner and Hillard Bell Huntington. What was once pure speculation is now understood to describe the interior of Jupiter and Saturn. Most of what fills those planets is metallic hydrogen, a state of matter completely inaccessible to human experience on Earth. Since Jupiter and Saturn are the largest planets in the solar system, this means most of the planetary material in our solar system exists in a form we have never touched, never seen, never truly grasped. NASA's Juno mission, launched in 2011 and powered entirely by solar energy, carefully mapped Jupiter's gravitational environment to peer inside. What it found suggests Jupiter has no solid surface, just an inferno of gradually shifting temperatures, pressures, and densities, blending from gas to liquid to metallic states without any clear boundary. Batuta had spent the better part of a century navigating the outer solar system, drilling through Europa's ice, dispatching semi-autonomous probes into Jupiter's metallic hydrogen interior, and skimming through Saturn's storm systems. Having proven its ingenuity and patience, it was huygens permitted to pass through the gates of the solar system. As it prepared for the crossing, the probe reflected on the pioneers who had gone before it. Cassini, Huygens, and Juno and their predecessors, the Voyager probes, launched decades before and still traveling long after their creators had gone silent. Batuta fashioned a thin metallic wire and unspooled it behind the spacecraft until it stretched 1,000 kilometers, a long, simple antenna. Through it, Batuta listened to the cosmos. It heard the groans of giant molecular clouds, the screams of stars being torn apart by black holes, the subtle hum of the Milky Way's magnetic field, and the drumbeat rhythm of distant pulsars. A universal symphony, the perfect soundtrack for the first leg of its journey. We know the moment Voyager 1 crossed into interstellar space because of plasma. The entire solar system sits within a bubble of particles streaming outward from the sun. The solar wind. Eventually, that wind slows enough that it can no longer push against the interstellar medium, and the flow comes to an abrupt halt at what's called the termination shock. Voyager 1 detected this boundary at a distance of 94 astronomical units from the Sun. Beyond the termination shock lies the heliosheath, where solar wind and interstellar medium mix. And at the outermost edge of that region sits the heliopause, the true boundary between the solar system and interstellar space. Voyager 1 crossed that boundary on August 25, 2012, at an incredible 18 billion kilometers from the Sun. There, it found interstellar space to be genuinely different, because beyond the heliopause, the Sun's protective magnetic field no longer shields against the toxic flood of cosmic rays that permeates the rest of the galaxy. Cosmic rays are among the most energetic particles in the universe. In 1912, Austrian physicist Victor Hess demonstrated, by carrying instruments in a hot air balloon to an altitude of 5 kilometers, even during a solar eclipse, so neither Earth nor Sun could be blamed, that the excess radiation ionizing the atmosphere had to come from space. The discovery earned him the Nobel Prize in 1936. Just about every high-energy process in the universe creates cosmic rays, stellar surfaces, supernova explosions, quasars, magnetars, and hypernovae. Because they carry electrical charge, they deflect and spiral in magnetic fields. Our sun creates a protective magnetic bubble around the entire solar system. Earth's own magnetic field provides a second layer of defense, but neither is perfect. High-energy particles still pass through a human body roughly once per second. Most are harmless, but occasionally one damages a strand of DNA or oxidizes a molecule in a cell, potentially triggering a replication error. In 2023, Voyager 1 went silent for 5 months, possibly a consequence of cosmic ray damage to its computer systems. Past the heliopause, not even the sun can offer shelter. Even in the deep cold beyond the heliopause, there are objects. Lonely residents, whose only knowledge of the sun is a single point of light, slightly brighter than the rest. In 1929, the year before he discovered Pluto, young astronomer Clyde Tombaugh was reportedly told by a senior colleague that if any more planets existed, they would have been found already. Tombaugh ignored the advice. Pluto appeared as a faint dot, revealing its existence only through its subtle movement against the background stars. Over the following decades, astronomers speculated that Pluto was not alone, that a whole population of objects might inhabit the fringes of the solar system. In 1992, astronomers David Jewitt and his graduate student Jane Liu confirmed the hypothesis after 5 years of painstaking searches. Their discovery, later named 15760 Albion, was the first confirmed member of what we now call the trans-Neptunian objects, a population stretching from about 30 astronomical units to hundreds of thousands of astronomical units, spanning subregions known as the Kuiper Belt and the Scattered Disk. On New Year's Day, 2019, NASA's New Horizons spacecraft slipped past Arrokoth, a trans-Neptunian object only a few dozen kilometers across. Arrokoth's peculiar elongated shape tells a story of ancient collision. Two icy bodies that found each other in the abyss long ago, colliding at such low speed that the ice between them melted and immediately refroze, bonding them together for billions of years. Neptune's gravity dominates this realm. Most of these objects live quiet, isolated lives, never encountering another for millions of years. But occasionally Neptune's pull destabilizes one, transforming it into a comet, a ball of ice and rock that loops toward the sun, evaporating a little more with every passage. And yet, even this is not the true edge of the solar system. In 1950, Dutch astronomer Jan Oort proposed that long-period comets, those that take thousands of years or more to complete a single orbit, couldn't have originated from a flat disk-like structure. They came from every direction in the sky, suggesting a spherical reservoir encircling the sun on all sides. Oort named it the Oort cloud, a vast shell of icy bodies, bound by the sun's gravity, but sitting in conditions that are essentially interstellar. No object has ever been directly observed within the Oort cloud itself. Its members are simply too far away and too small for even our most powerful telescopes. But based on the size and frequency of long-period comets, the cloud likely contains around 5 Earth masses of material. Its inner boundary sits roughly 2,000 astronomical units from the Sun, 20 times farther than the heliopause. Its outer edge remains unknown, with estimates reaching up to 3 light-years, most of the distance to our nearest neighboring star. Beyond our solar system lies a neighborhood of stars, many formed from the same ancient cloud of gas and dust that gave birth to our Sun. Within a 20 light-year radius, there are 131 known objects: stars, white dwarfs, brown dwarfs, and sub-brown dwarfs straddling the boundary between the largest planets and the smallest stars. Surrounding this stellar neighborhood is a region called the local bubble, a vast cavity in the interstellar medium extending roughly 1,000 light-years on a side. Its plasma density is about 1/6 of the material surrounding our solar system. Our Sun has been traveling through this bubble for the past 5 to 10 million years. Most astronomers believe it was carved out by a sequence of supernova explosions detonating one after another, remnants of which have been found embedded in the ocean floor and in Antarctic ice, as rare isotopes of iron, manganese, plutonium, and aluminum. After 10,000 years of travel, Batuta was now deep in the void, the great emptiness between the stars. Its interstellar journey had truly begun. 100,000 years had passed since Batuta left Earth. Roughly halfway through its journey to a star 90 light-years away, it had changed course. A detour that cost 8,000 years but proved worth every moment. The destination was Algol, the demon star, 3,200 years ago. An Egyptian calendar of auspicious and inauspicious days listed this star as one that brought misfortune. In Greek mythology, it represented the severed head of Medusa, held triumphantly by the hero Perseus. In Chinese astronomy, the star's name translated roughly to piled up corpses. Its formal designation was Beta Persei, the second brightest star in the constellation Perseus. In the 17th century, Italian astronomer Gimignano Montanari noticed something unsettling. Algol changed its brightness. A century later, astronomers confirmed the changes were periodic. Roughly every 10 days, Algol dimmed for a period of hours before recovering. It wasn't until the 19th century that Harvard Observatory astronomer Edward Pickering, who famously assembled a team of women, his Harvard computers, to analyze stellar spectra, discovered the cause. Algol wasn't one star but two, a bright, hot primary orbited by a smaller companion. From Earth's perspective, when the companion crossed in front of the primary, the whole system appeared dimmer. But this tidy explanation conceals a history of violence. Algol A, the larger, brighter star, is still in its main hydrogen burning phase, while Algol B, the smaller companion, is a subgiant nearing the end of its life. This is backwards from what physics predicts. Larger stars burn through hydrogen faster and should age more quickly. The explanation is a process called mass transfer. When Algol B expanded into a red giant at the end of its main sequence, it overflowed the gravitational boundary between the two stars, allowing its companion to steal hydrogen, like a stellar vampire preying on its own sibling. Over time, Algol B was stripped of so much material that it is now the smaller of the two. Algol is just one of many multi-star systems. The simplest are binary pairs. Either two stars orbiting a shared center of mass or a smaller star orbiting a larger one. The most complex systems known host up to 9 stars in intricate, interlocking gravitational dances. Alpha Centauri itself is a triple system. 2 stars in close mutual orbit with a third, Proxima Centauri, circling them from a great distance. In the 19th century, a self-taught German mathematician named Friedrich Bessel, who had dropped out of school at 14 due to his distaste for Latin and taught himself navigation through a fascination with sea voyages, became the first person to accurately measure the distance to another star. His target was 61 Cygni, nicknamed the Flying Star for its unusually rapid apparent movement across the sky. Bessel correctly guessed that fast apparent motion meant the star was relatively nearby. When his measurements were complete, the distance was so vast he needed a new unit of measurement to describe it. He created the light year, the distance light travels in a single year. His result: 61 Cygni was approximately 10 light years away. Among the most spectacular stars in the sky, though not the nearest, is Betelgeuse, the 10th brightest star visible from Earth. Despite lying roughly 450 light years away, it is so massive and so enormously bloated that it would engulf Mercury, Venus, Earth, Mars, and most of the asteroid belt if placed at the center of our solar system. Its surface boils and churns, distorted by violent internal convulsions. In late 2019, Betelgeuse unexpectedly dimmed dramatically, from one of the top 10 brightest stars in the sky to below 20th place, likely due to a massive eruption of superheated plasma that temporarily formed a dust cloud obscuring its surface. Once the debris cleared, it returned to full brightness. Betelgeuse will not last. Within the next 100,000 years, it will explode as a supernova. Theoretical calculations suggest it will peak at roughly the brightness of a half moon, bright enough to read by at night, before fading within weeks into invisibility. The constellation of Orion will forever lose his shoulder. Proxima Centauri, our nearest stellar neighbor, is far more modest, a small red dwarf invisible to the naked eye. But it carries something remarkable: a planet. Proxima b, a rocky world roughly Earth-sized, orbits within the star's habitable zone. It is the closest known candidate outside our solar system for a world that might support life. But life there would not be easy. Red dwarf stars are temperamental. They erupt in electromagnetic storms, blasting their nearby planets with intense radiation. Star spots can cover half their surfaces, and at such close orbital distances, Proxima b orbits at only 5% of the Earth-Sun distance. The planet is almost certainly tidally locked, with one face permanently turned toward its star and the other in permanent darkness. One hemisphere baked, one hemisphere frozen, yet even this doesn't automatically make such a world dead. Computer models show that with enough water and atmosphere to circulate heat, even a tidally locked planet could maintain conditions suitable for life in the boundary zone between permanent day and permanent night. A narrow twilight band where temperatures remain stable, caught between roasting and freezing. There are at minimum several hundred billion planets in the Milky Way alone, at least one per star, possibly far more. Among them are duplicates of our solar system, with rocky inner planets and distant giants. There are systems like TRAPPIST-1, where 7 rocky planets orbit in tight formation around a dim red dwarf, 3 of them potentially within the habitable zone. There are gas giants so close to their stars they are actively being destroyed, their atmospheres bleeding away into space. There are Haitian worlds, planets wrapped in thick hydrogen atmospheres above global oceans. There are planets so hot they glow red. There are worlds locked entirely in ice. And there are rogue planets, worlds ejected from their home systems, drifting alone, and cold through the galaxy, orbiting nothing. Batuta could not catalog them all. After a brief detour to the Algol system, it resumed its planned trajectory, a string of stellar systems stretching inward toward the galactic core. For the first million years, there would be little to distinguish one system from the next. No signs of life, no exotic physics. For that, it would have to travel much farther still. 1 million years since awakening. Batuta marked the occasion quietly, nestled near a protoplanetary disk in the Scutum Centaurus arm, roughly 15,000 light-years from the galactic core. The disk was in its earliest stages of planetary formation, and the process was too remarkable to pass up. Even with all of recorded human knowledge available to it, no civilization had ever watched a solar system being born in real time. Batuta decided to wait. The story of planet formation is the story of life, and that story begins with 5 elements: hydrogen, carbon, oxygen, nitrogen, and phosphorus. Without them, life as we know it is impossible. Hydrogen was the simplest to explain. It emerged in the first few minutes after the Big Bang, when a soup of quarks and gluons condensed into hydrogen, helium, and trace amounts of lithium and beryllium. As the universe expanded and cooled, those reactions ceased, freezing the light element population in place. But where did everything else come from? Carbon, iron, gold, oxygen, the rest of the periodic table? The answer came in 1957 from a landmark paper authored by 4 scientists at Cambridge: Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, known together as the B2FH paper after their initials. Their work demonstrated that it is stars that forge the elements. All stars burn hydrogen in their cores, leaving behind helium ash. Toward the end of their lives, stars resort to burning that ash, fusing helium into carbon and oxygen. For massive stars, that chain continues further. Carbon into oxygen, oxygen into silicon, and finally, silicon into iron. And when stars die as supernovae, the explosive energy produces even heavier elements, scattering them into the interstellar medium to seed the next generation of stars and planets. Since that landmark paper, the story has been refined. In 2017, the detection of a kilonova, the merger of 2 neutron stars, added a new chapter. Events like these produce vast quantities of gold, platinum, and other heavy elements in minutes. But the core story told by the Burbidges, Fowler, and Hoyle remains fundamentally unchanged. With the death of every star, the cosmos grows richer. Nebulae dot the Milky Way's spiral arms like ornaments, no 2 alike. Some are stellar nurseries, clouds of gas and dust, collapsing under gravity to birth new suns. Some are stellar funerals, the scattered remnants of stars that have already died. Planetary systems begin as diffuse clouds of hydrogen, helium, and heavier elements. In the early 1900s, British physicist Sir James Jeans identified how these clouds could collapse. Any disturbance in the balance could trigger a runaway gravitational collapse. As material falls inward, most of it gathers at the center, heating to extreme temperatures to form a protostar. The surrounding material flattens into a spinning disk, a protoplanetary disk. Within the inner regions of that disk, close to the forming star, only heavy elements like iron, carbon, and silicon can survive the heat. These form the raw material of rocky terrestrial planets. Farther out, where the young star's heat is too faint to evaporate them, ices of water, ammonia, and nitrogen mix with dust to form much larger planetesimals, the seeds of gas and ice giants. The first of these to reach sufficient size wins the gravitational lottery, sweeping up enormous envelopes of gas. The competition for whatever remains drives chaotic interactions, ejecting some planetesimals entirely. In our own solar system, the giant planets likely formed much closer to the Sun, then migrated outward as the disk cleared. There may have been a fifth giant planet that was ejected in that chaotic process. Planets can even form without a star at all. Some rogue worlds wander the galaxy alone, flung out from their birth systems by gravitational violence. And between true planets and true stars lie the enigmatic brown dwarfs. Too large to be planets, too small to sustain hydrogen fusion, quietly cooling in the dark. After nearly 10 million years, Batuta reached the outskirts of the Milky Way's core, an elongated bar of densely packed stars and ancient light. The journey hadn't been without incident. Deep in the Norma arm, Batuta had detected a faint radio signal whose pattern could only be artificial. Another probe launched by humanity long before, leaving encoded signs in the deep sky. Now at last, Batuta turned toward the galactic center and its true objective. Sagittarius A, the supermassive black hole at the heart of the Milky Way. Along the way, it paused to study the ancient ones. Stars so old they strain our understanding of cosmic history. Among them, HD 40283, informally called Methuselah, after the biblical figure said to have lived 969 years. In some estimates, this star appeared to be older than the universe itself, a possibility that sent a ripple of unease through the astronomical community. Had something gone wrong with Big Bang cosmology? Was stellar physics fundamentally misunderstood? The answer, as is often the case in astronomy, came down to uncertainty. Methuselah is undeniably ancient, among the oldest known stars in the galaxy, but it formed after the Big Bang. The problem is that the uncertainties in age estimation are large enough that the star can appear older than the universe when those error bars stack unfavorably. Stars can be classified by their heavy element content. Population I stars, like our Sun, have relatively high concentrations of metals, the astronomical term for all elements heavier than helium. Population II stars, like Methuselah, are older with fewer heavy elements. And population III stars, the very first generation, had none at all. Population III stars have never been directly observed. They likely formed when the universe was very young and the interstellar medium contained only hydrogen and helium. Without metals to moderate their reactions, or allow their gas clouds to cool and fragment, these first stars may have been enormous, possibly 100 times the mass of the Sun, perhaps far more. At those scales, they would have burned through their fuel in mere millions of years, dying long before the first galaxies had fully assembled. Telescopes like the James Webb Space Telescope now search for traces of these ancient giants in the faint light coming from the universe's earliest epochs. Each generation of stars has been slightly richer than the last, inheritors of the heavy elements scattered by every preceding death. Not all stars end the same way. For the smallest, the red dwarfs, the end is quiet. They burn slowly and dimly, living for trillions of years before simply fading out. There are currently no dead red dwarfs in the universe. The cosmos isn't old enough for any to have finished yet. Medium-sized stars like our Sun have a more dramatic fate. As hydrogen runs out in their cores, they swell into red giants, contracting and reigniting in a series of violent transitions before finally shedding their outer layers and leaving behind a white dwarf. A compact, incredibly dense remnant about the size of a terrestrial planet, composed of carbon and oxygen. When white dwarfs were first confirmed in 1916, many astronomers refused to believe the results. Estonian astronomer Ernst Öpik calculated that some stars had densities more than 25,000 times that of the Sun. The response from much of the scientific community was dismissive, but Öpik was right. White dwarfs are genuinely that dense. Freshly emerged from the nuclear furnace of a dying star, white dwarfs start with temperatures exceeding 10 million Kelvin, hot enough to flood surrounding space with X-rays. Those X-rays energize the gas shed by the dying star, exciting electrons to higher energy states, which then release light as they fall back down. The result is a planetary nebula, a glowing shell of ionized gas around the cooling white dwarf, each one unique in shape and color. After about 10,000 years, the white dwarf cools enough to stop emitting X-rays, the nebula fades, and the display is gone forever. But when a white dwarf has a companion star, things can turn explosive. If the companion swells into a red giant and transfers hydrogen onto the white dwarf's surface, that hydrogen can be compressed to densities sufficient to trigger nuclear fusion, a flash of thermonuclear energy known as a classic nova. If the hydrogen accumulates faster than it burns off, the event can escalate catastrophically. A runaway nuclear detonation races through the white dwarf's interior, obliterating the entire star in a single titanic explosion, a Type Ia supernova. These events can outshine the combined light of hundreds of billions of stars. For stars more than 8 times the mass of the Sun, the end is different. These stars cycle through fusion phases of increasing inefficiency: hydrogen, then helium, then carbon, oxygen, neon, and silicon. The timescales collapse catastrophically. Millions of years for hydrogen, then thousands, hundreds, days, and hours. And then comes iron. Iron fusion doesn't release energy, it absorbs it. With nothing left to counteract gravity, the core collapses. In seconds, the entire star falls inward. Pressures become so extreme that electrons are forced into atomic nuclei, merging with protons to produce neutrons. The core becomes a sphere only a few kilometers across, composed almost entirely of neutrons. The surrounding star crashes inward at a substantial fraction of the speed of light. And when it strikes the newly formed neutron core, it rebounds outward in a shockwave that tears the star apart. 1054 CE, Chinese astronomers recorded the sudden appearance of a brilliant new star, bright enough to see in daylight, visible for weeks. At the same time, half a world away, the ancestral Pueblo people of what is now New Mexico created a pictograph commemorating the same event. Today, the sky where that light once blazed is occupied by the Crab Nebula, still expanding, still glowing, a frozen moment of stellar death visible from Earth with a small telescope. Supernovae are not merely destructive. They are also creative. The shock wave racing outward through the dying star's material triggers nuclear reactions that forge the heaviest elements: gold, platinum, and uranium, scattering them into the interstellar medium, ready to be incorporated into the next generation of stars and planets, including, eventually, us. Batuta hung at the edge of the abyss. Sagittarius A was dead ahead. The environment surrounding the supermassive black hole was the most continuously energetic place in the entire galaxy, a maelstrom of plasma, radiation, and gravitational forces beyond any ordinary scale. And beneath all of it, quiet and absolute, was the black heart itself, a boundary in space-time cutting off everything within from everything without. For a brief moment, Batuta was tempted. The singularity at the center held the answer to quantum gravity, the long-sought reconciliation of general relativity and quantum mechanics. But crossing the event horizon would mean never returning. Whatever was learned inside could never be shared. The earliest hints of the black hole at the Milky Way's center came in 1933, when radio astronomy pioneer Carl Jansky noticed unusually strong radio emissions coming from the direction of the galactic center. Decades of increasingly detailed observations narrowed the source to a compact region in the constellation Sagittarius, eventually designated Sagittarius A. The asterisk added because the object was considered particularly exciting. Confirmation of a supermassive black hole required watching the stars around it. 2 independent research teams, one led by German astronomer Reinhard Genzel, the other by American astronomer Andrea Ghez, spent decades developing the technology needed to track individual stars orbiting the galactic center in real time. Some of those stars reached peak velocities of 30% the speed of light. Their orbits gave the first precise measurement of Sagittarius A(Al's) mass. Just over 4 million solar masses, with an event horizon roughly 44 million kilometers in radius, more than 30 times the width of our Sun. If placed in our solar system, Sagittarius A would swallow Mercury entirely. Black holes are extraordinary objects. They are singularities, defects in space-time. Yet they possess mass, composed of everything that has ever fallen into them. They consume anything: radiation, dark matter, subatomic particles, molecular clouds, entire stars, other black holes. The smallest known black hole, GROJ WIC 65540, contains only about 6 solar masses. The largest with a well-confirmed mass estimate is Tion 6N18, weighing in at approximately 66 billion solar masses. With an event horizon so vast that you could travel all the way to the orbit of Pluto and still be only 1/80th of the way to its boundary. Lone black holes are nearly invisible. Unless actively consuming material, they emit nothing. In 2023, astronomers confirmed the first known isolated stellar mass black hole using microlensing, where the black hole's gravity briefly brightens the light of a background star. The Milky Way is estimated to contain around 100 million black holes in total. When two black holes merge, they do so in near total silence. No flash of light, no visible explosion. Their only emission is gravitational waves, ripples in the fabric of space-time itself. On September 14, 2015, the LIGO Gravitational Wave Observatory, capable of measuring a change in distance smaller than 1/10,000th the width of a proton, detected the merger of two black holes hundreds of millions of light years away. It was the first direct confirmation of gravitational waves, validating a prediction Einstein had made more than a century earlier. Batuta completed its approach to Sagittarius A carefully. Years of preparation reduced to a single precise maneuver. At exactly the right moment, it adjusted course and was free, accelerating outward and away from the galaxy. 40 million years of nearly nothing. The spiral of the Andromeda galaxy is growing slowly larger ahead. The Milky Way is shrinking behind. For the first time in its existence, Batuta felt genuinely alone. The space between galaxies is not truly empty. It is filled with the warm, hot intergalactic medium, a diffuse plasma with temperatures between 100,000 and 10 million Kelvin. Believed to contain nearly half of all ordinary matter in the universe, it is almost impossible to directly observe. So thin, so spread out, that despite its high temperature, its overall brightness is negligible. Batuta pressed on toward Andromeda, a larger, more active galaxy than the Milky Way, home to more exotic objects and more energetic events. It found what it was looking for. In 1967, graduate student Jocelyn Bell, working at Cambridge under radio astronomer Anthony Hewish, noticed something unusual in the telescope data. A strange, repeating signal, appearing with a periodicity of exactly 1.337 seconds. Initially skeptical, the team verified the signal with another instrument. It was real, repeating, and unmistakable. Soon enough, the source was identified as something entirely natural. A pulsar, a rapidly spinning neutron star emitting beams of radio radiation from its magnetic poles. As the star rotates, the beam sweeps across the sky like a lighthouse. If Earth lies in its path, we see a regular pulse. Neutron stars are the densest objects in the universe short of black holes. Typically containing 1 to 2 times the mass of the Sun compressed into a sphere no wider than a typical city, they are essentially enormous atomic nuclei. Their gravity is so strong that light can orbit around them. The tallest mountains on their surfaces are fractions of a millimeter high. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second, 43 0 revolutions per minute, faster than a jet turbine. Magnetars take the already extreme properties of neutron stars to a level that seems almost impossible. A special dynamo mechanism operating within a rapidly rotating newborn neutron star can amplify its magnetic field to extraordinary strength. A typical magnetar hosts a magnetic field roughly 1 trillion times stronger than Earth's. Fields of this intensity stretch and deform atoms into needle-like shapes. Molecular bonds collapse. Even the vacuum itself becomes distorted. Approaching a magnetar is a death sentence. Its X-ray emissions, radiation beams, and gamma-ray flares would overwhelm any shielding. But eventually, all magnetars fade, their spinning slows, and the star settles into a quieter existence. Batuta was not easily impressed, but the magnetar managed it. In 1963, the United States and the Soviet Union signed the Partial Nuclear Test Ban Treaty, but the US remained suspicious of Soviet compliance. To monitor potential secret nuclear tests on the far side of the moon, the American military launched the Vela satellites, designed to detect gamma rays produced by nuclear blasts. The satellites never detected a weapon. But on July 2nd, 1967, they recorded something else entirely: a brief, brilliant burst of gamma rays. The event was kept classified until a dozen similar detections followed, at which point scientists convinced military authorities to release the findings. And so, gamma ray bursts entered the scientific literature. Astronomers now classify gamma ray bursts into two types. Short GRBs, lasting less than about a third of a second, are most likely produced by kilonova events, the merger of two neutron stars. In 2017, astronomers confirmed this when the gravitational wave signal from neutron-star merger arrived at Earth almost simultaneously with a short GRB, triggering a worldwide observational campaign that produced over 100 published papers. Long GRBs, spanning from a couple of seconds to several hours, are thought to arise when the core of a massive dying star collapses to form a black hole. Jets of charged particles are launched outward from the poles at nearly the speed of light, slamming into surrounding material and producing a flood of gamma rays. These events can release more energy in seconds than our sun will radiate over its entire 8 billion year lifetime. Fast radio bursts. FRBs are millisecond-long radio flashes of extraordinary power, originating from across the universe. First discovered in 2007, buried in archival pulsar data, FRBs have been frustratingly elusive. In 2020, astronomers identified a magnetar within the Milky Way that produced both X-ray flares and radio bursts simultaneously. The strongest evidence yet that at least some FRBs are caused by magnetar glitches, sudden shifts in the neutron star's crust that cascade through the magnetic field, dumping a sun's worth of energy into space in the blink of an eye. In 1962, astronomers pinpointed the precise locations of several mysterious compact radio sources and captured their spectra. One astronomer, Martin Schmidt, made a radical proposal. These objects showed emission lines from ordinary hydrogen, but shifted dramatically toward longer wavelengths. The implication: they were unimaginably far away, hundreds of millions of light years, and unimaginably powerful, outshining entire galaxies from a volume no larger than a solar system. They became known as quasars, quasi-stellar objects. What could power something so luminous from such a small volume? In 1963, physicists Edward Salpeter and Yakov Zeldovich proposed that quasars were powered by supermassive black holes. At the time, black holes were still theoretical, but the evidence eventually prevailed. The mechanism is gravitational. Material falling toward a supermassive black hole forms a swirling accretion disk. As it spirals inward, it compresses and heats to temperatures of quadrillions of degrees, radiating at all wavelengths. A typical quasar can outshine over 1,000 galaxies. And unlike the brief explosions of supernovae, a quasar can sustain this output for millions of years. In 2019, the Event Horizon Telescope, a network of radio telescopes spanning the globe, produced the first direct image of the plasma surrounding a supermassive black hole, the one at the center of Messier 87, 54 million light-years away. At the center of the glowing ring of hot material was the shadow of the black hole itself, the first visual confirmation of a feature physics had long predicted. Deep within the boot's void, Batuta detected something it had not expected. A signal unlike any known astrophysical template. Not a pulsar, not a gamma ray burst, not any cataloged source. It had seen similar anomalies before and learned to ignore them. But this one lay along its route home, and it seemed different. It investigated. What it found pointed to coordinates deep within the void, a location where there should be nothing at all. And the evidence converging on that location told a story about something that should not exist in the modern universe: a cosmic string. The concept was proposed in 1976 by British physicist Tom Kibble. His paper predicted something genuinely bizarre: one-dimensional topological defects in space-time created during the earliest phase transitions of the universe. When the fundamental forces of nature fractured apart from one another, understanding why requires going back to 1979, and a physicist named Alan Guth. In the late 1970s, cosmologists working to extend the Big Bang model into its earliest moments encountered a troubling prediction. The exotic physics of the early universe should have produced vast numbers of magnetic monopoles, point particles carrying only a single magnetic pole. The problem was that not a single monopole had ever been detected. On an otherwise unremarkable December morning in 1979, Guth woke with an idea. He rushed to his office and worked out a mechanism he called inflation, a brief period of exponential expansion in the universe's first fraction of a second, during which the cosmos grew by an enormous factor. Inflation would dilute the monopoles to near-zero density within any observable volume. It would also explain why the universe appears geometrically flat at the largest scales, and it would provide the seeds of all cosmic structure. The fluctuations in density that gravity would later amplify into galaxies, superclusters, and the cosmic web. Guth drew a box around the idea in his notebook and wrote "spectacular real association" in capital letters above it. That notebook is now on permanent display at the Adler Planetarium and Astronomy Museum in Chicago. But inflation, while solving the monopole problem, could not eliminate another class of defect: cosmic strings. Unlike monopoles, which inflate apart from each other, cosmic strings stretch along with the expansion of the universe, becoming longer, not rarer. If they formed in the early universe, some should persist to the present day. They should be everywhere, and yet none have ever been observed. Cosmic strings, if they exist, are perhaps the strangest objects in the universe. They are not made of any substance. They are defects in the fabric of space-time itself. The same way a crack in ice isn't made of anything, but is simply ice in an unusual arrangement. Their width is no greater than a proton's, but they may extend for hundreds of millions of light years, possibly spanning the entire observable universe. A single kilometer of cosmic string would outweigh the entire Earth. If one were to pass through a planet, it would slice through without slowing, splitting worlds without even noticing. They vibrate, rippling at the speed of light. When cosmic strings cross each other, they break apart, releasing bursts of energy. We do not fully understand how they interact with ordinary matter. Virtually everything known about them comes from theoretical models, extrapolated from our still incomplete understanding of the physics of the universe's earliest moments. Cosmic strings are the physical embodiment of our ignorance. They represent the limit of what known physics can describe. Batuta shed everything it could: its outer sensors, supply sections, and extended structures, trimming itself to its core, its memories, its identity, and its founding mission. Then it turned to face the string. As it approached, it noticed something unexpected. The string barely registered on any conventional instrument, almost ghostly, nearly transparent, perceptible. Only in the way it split and magnified background light, duplicating stars behind it like a gravitational lens stretched across millions of light years. And yet, it was real, undeniable, ancient beyond measure. For what felt like an eternity, Batuta simply watched. Nothing it had ever found. Not the magnetar, not the quasar jets, and not the galactic core compared to this. It was like staring back almost 14 billion years to the first moments of existence. If there were an answer anywhere in this universe to humanity's desperate need, some new physics, some key to crossing the interstellar void, it would be here, in this flaw in spacetime made manifest. Batuta accelerated toward the string. In a blink, it slipped into darkness. Its final thought was one it had carried with it since the very beginning. Far from home, untouched by remote events, the Voyager, bearing the memories of a world that is no more, will fly on.